Hello and welcome to another exciting session on learning statistics. After this session, you will get clarity on how to apply the F distribution, F for Frank, F distribution. Conduct hypothesis testing with ANOVA and interpret results from confidence intervals and p-values in various statistical scenarios. More specifically, we will learn how to use F distribution to test if two population variances are equal. We will also learn how to use analysis of variation. Sorry, analysis of variance. Analysis of variance is in short form is called ANOVA, ANOVA, to test if three or more population means are equal. So if you can see this here, what you have is AN analysis of variance. So ANOVA in short form, AN for analysis, O for off, VA for variance. That's what ANOVA is. Finally, we will learn how to use confidence intervals to compare differences between pair of population means. Okay, so let's first talk about what F distribution is. Um, the F distribution is a continuous probability distribution that arises uh, frequently in statistics, particularly in the context of comparing variances. It is used to test whether two population variances are equal and in analysis of variance to compare the means of three or more populations. Um, so the background about this term called ANOVA, F distribution, why this is called F distribution. The F distribution is named after Sir Ronald A. Fisher, who was a British statistician um, and scholar who developed this F distribution for analyzing variances in experiments. Fisher introduced the F distribution in his work on analysis of variance called ANOVA, a method for testing the hypothesis that the means of multiple groups are equal by comparing their variances. The F word in quote unquote F in F distribution stands for Fisher, the person's name, initial of person's name, Fisher, honoring that person's contributions to this theory. So I hope you get the background of F distribution in statistics. So let's see what we can look more into this. So this is what we were talking about. So F distribution has several properties of characteristics that we need to consider. So the F distribution is positively skewed. Is positively skewed because it has long tail on the right hand side. See this, when you have a long tail on the right hand side, this kind of distribution is called positively skewed. And distribution is continuous, as you can see that it's a continuous distribution, and non-negative. So the statistic in this case, F statistics, cannot be negative. So F statistic is what we call F values. They are always greater than or equal to 0. As you can see, there is nothing on the left hand side. Everything is on the right hand side, which is a positive quadrant here. And now, so Let's see further actually. Yeah, so and also degrees of freedom. Degrees of freedom, the shape of the distribution depends on degrees of freedom in both the numerator and the denominator of the F ratio. Because I'll talk in a moment actually about what I'm talking about F ratio is. So let me first describe what the degrees of freedom refers to. So degrees of freedom refer to the number of independent values or quantities that can vary in a statistical calculation while still adhering to any constraints or relationships among data. Essentially, uh, it represents the number of values that are free to change when estimating a statistical parameter. So the formula or a relationship that you can use to figure out degree of freedom is basically you look at the sample size and subtract one from it. If n is a sample size, then degrees of freedom are written as df. So df is equal to n minus 1. So always like that. And the last characteristics of this is that F distribution is asymptotic. What it means is that as the F value increases, the curve approaches horizontal axis, but it never touches it. It never touches, but it approaches. Basically, it keeps going all the way to infinite plus infinity. And well, F distribution is very useful in hypothesis testing to determine if the observed differences are statistically significant. We will look at some examples to understand what it means. All right, so to use F distribution, the populations must follow a normal distribution. A normal distribution. But you can see this is shape of these curves. Actually, they all follow normal distribution, although it is skewed to right hand side, but the distribution is normal. So basically, the population must follow a normal distribution, and the data must be at least on an interval scale. So F value can range from zero, starting from zero to positive infinity. So all the way to infinity, because the curve F distribution curve never touches the horizontal axis. It keeps going on up to plus infinity. And the smallest value they can have is zero. So F distribution has a long tail, as I said, no right hand side. And as the value of F increases, the curve approaches, but never touches horizontal axis, as I said. So now, if you see these numbers here, degrees of freedom 29 versus 28, 19 versus 6, 6 versus 6. So what it is, look, this distribution, let's say, look at this distribution with the degrees of freedom 29 and 28. In this case, the numerator is 29. This means the numerator is 29 for F statistic, and denominator is 28. Here, denominator is 19 and denominator is 6. And in this case, third one, you have numerator is 6 and denominator is also 6. Okay. So, and the shape of the distribution changes as the values change for degrees of freedom. The shape of the distribution shifts as the degrees of freedom change, and as the degrees of freedom increase for both numerator and denominator. So you can see that F distribution, as the numbers change, basically as the degrees of freedom increase for both numerator and denominator, F distribution slowly starts resembling like a normal distribution. All right. So let's see what we have next is comparing two population variances. We can use F distribution to test whether the two population variances are the same if the sampled populations follow the normal distribution. We can select a random sample of N1, say N1 from one population and say N2 from other population. Here's we look at this example here. First of all, let's see what is a test statistic for comparing two variances. So in this case, because F distribution, we call it F statistic. The relationship is that it is given by square of standard deviation of one population divided by square of standard deviation of another population. So basically, I know the square when standard deviation squares give you variance. So that's what I mean. So the F ratio is calculated using the larger. You always use a larger variance as a numerator and a smaller variance as a denominator. And so the minimum ratio is 1. So basically, ratio should be at least 1. Okay. Again, we already talked about this variance actually. So standard deviation squared is equal to variance for any population. Now let's look at one example here. This is example here. Comparing the two population variances. So this example, Lammers Limos offers limousine services from government center in downtown Toledo, Ohio, to Metro Airport in Detroit. The president of the company is considering two routes. One is via US 25, another via I-75. He wants to study the time it takes to get to the airport using each route and compare the results. He collected the following sample data using the 10% or 0.10 significance level. Is there a difference in the variance in driving times for the two routes? So let's look at this. So here's two scenarios given to us. One is a US route 25, other is a 75, and these are the various times taken for to go to airport for each route. And the number of elements in the sample we have here. We have 1, 2, 3, 4, 5, 6, 7 here, and 1, 2, 3, 4, 5, 6, 7, 8 here. All right. So first of all, what we need is a standard deviation. We need a mean and standard deviation. So in mean, we can find population mean by summing all the individual numbers we have here, right? And dividing by the total number of elements here. So that's X bar is equal to sigma X divided by N. So we add these all up, actually under US route 25 gives us 408 divided by 7 gives us 58.29. So for interstate 70s, we can do the same thing for this side, and we get 59 as a mean value for this, right? This sample on this side. So we can find standard deviation. The formula we can use this formula for that, where X is any number in the sample, and X bar is a mean, and N is the number of size of sample, and we can find standard deviation. So we got standard deviation in each of the cases. So I hope so far so good on this one. Okay, so pretty straightforward. Okay, let's see. Next we have, and now we can use a hypothesis. We can use a hypothesis to process this hypothesis. So we can okay. So right now we can define our null hypothesis here and alternative hypothesis. H naught is a null hypothesis. We can say, because if you see this, what we're trying to do here is now find out if is there a difference. So is there a difference or not? So either is equal to or not equal to. There are two routes actually, whether they are equal to or not equal to. So we can say, well, we can assume that they are equal to. We can say, okay, sigma 1 square is equal to sigma 2 square. We can say they're equal to. And alternative hypothesis, then they are not equal to. Okay. So step 2 is finding, selecting the level of significance, and I believe it's given to us here 0.10. That's fine. Here given to us. Now we have to use F statistic for every F distribution. Let's see. Now we can use okay. First of all, we need to use the F distribution table. Because we need to look at the critical value for F distribution. And this kind of tables, as I said, no, all the tables can be found in the back of any statistics book, or you can just simply go on Google and find F distribution tables. They are readily available there. So since we use 2 degrees of freedom here, one is for numerator, other is for denominator. As you can see that this table allows us to pick each one of them. Okay, so and also I mentioned that the degrees of freedom can be found, like a DF can be found by subtracting 1 from sample size. So one sample for numerator, we sample size is the sample size. There is a sample size 7 and sample size 6, right? So we have 2 values here. One is for denominator, we have degrees of freedom in denominator is like 8 minus 1, and in a numerator we have 7 minus 1, 6. So we can look at 6 versus 7, and we get they intersect here. The 3.87 is the critical value that we need to consider. So what we need to do is once we have a critical value, we compare test statistic against the critical value that we have to use in this case. So basically, what we can see in step number 4, we can reject H naught, like the assumed situation. So H naught, the null hypothesis, if the ratio of the sample variance is greater than this critical value 3.87. So basically we go into rejection region. All right, so let's see what we get here. Okay, we get here, what we get here is we get step number 5. So we are here actually. So now we need to find is we need to find our F statistics. We know the number to compare against, but we need to know, okay, what is our F statistics here? The formula we know, as we saw before, is F is equal to S1 square divided by S2 square, and we know our we found these S1, S2, like 8.9 here, 4.3. We can use these values here, and what we get, F is equal to 4.3. So we need to compare F with this critical value belonging to these degrees of freedom we used for these 2 populations. So basically now the criteria to reject or select is that if F statistics is greater than 3.87, we should reject H naught, and it is greater than the critical value, and that means decision is to reject the null hypothesis because statistic is 4.3, which is greater than the critical value of 3.87. So basically, if we reject this, now what is the answer now? The answer is that there is a difference, right? There is a difference. So we conclude here that there is a difference in the variation of in the time to travel to the two routes. So Mr. Lammers now need to consider this in scheduling. It's pretty interesting problem, right? So let's see what we can get next here. Next, we're going to look at the analysis of variance, ANOVA. So what is ANOVA? So ANOVA compares two or more treatment means and used when populations are normally distributed, independent, and have equal variances, right? And so the sum of squares for total error and treatment helps in calculating the F statistic for the ANOVA table. So, and what is a treatment? We are talking about treatment. What is treatment? Treatment is a source of variation. Okay, and I'll show you what it means in the actual example in a moment. So basically, a one-way ANOVA can be used to compare two or more treatment means, and also we can go beyond that to comparing. Okay, so first of all, let's see actually how we can use it. All right, so let's see what we have here is. There are some assumptions that we need to consider for using ANOVA. Number one, the populations follow normal distribution, okay, and they have equal standard deviations for all the populations we are trying to compare, and the populations are independent. These three considerations. Okay, so now let's look at one example. Let's look at one example. So here, Joyce Coleman manages a regional financial center. She wishes to compare the productivity as measured by the number of customers served among three employees. So there are three employees, and each employee is serving customers. Okay, so the study is conducted for 4 days. 4 days are randomly selected, and the number of customers served by each employee is recorded. So, like for example, this guy Wolf, in day one serves 55 customers, then day 2 54, day 3 59, and day 4 56. Similarly, other people, right? So this is the problem. So Joyce wants to compare is she wishes to compare the productivity, so based on what data is given to us. Let's see how we can do that. So we're going to use ANOVA test. ANOVA test. Let's see how it is being used. ANOVA test. Okay. So this is a given data to us. Now, first we need to find is the overall mean of 12 observations. So there are 4 here, 4 for Wolf, 4 for White, and 4 for Prosa. Total 4 times 3, 12 observations. So when we find the overall mean, means adding all these values divided by 12 gives us 58. Now, okay, we got this overall mean. Okay, now we need to find the difference between each of these values and the overall mean. Then what we need to do is square those differences and add them up. So for example, 55 minus 58, right? Then we square it. Okay, then 54 minus 58, the difference we square it, and keep doing that. All the different squares of the differences, we add them up. And what we get here is 1082 total. Okay. And this is we call total variation. So, and we define as total variation. So total variation is the sum of the squared differences between each observation and the overall mean, like we had here. Okay. Now, once we have that, now we can now break this into two components: variation due to treatment variation and random variation. As I said, the treatment variation means like when source changes. Source means when we switch from one person to another, right? That's called treatment variation. Random variation is when we go from one observation to another observation. So that's what I defined as the sum of square differences between each treatment mean and the grand or overall mean. So basically, the difference between that each treatment mean. So mean of this minus the mean of the overall. That's what I mean. So random is like a sum of square difference between each observation, each of these values, and treatment mean. Treatment mean, basically the mean of each, that mean of this, mean of this, mean of this. So these are these different things are this different categories or different people we call treatment, right? So let's take a look at an example to understand better. So, I mean, we are following example. Basically, what we can do next, actually following this this information. So we have this data given to us. Now, the overall mean we know that is 58, and total variation is 1082. So how we break this this into two components: variance due to treatment of variation and a random variation. So now let's look at what is variance due to treatments. So variance due to treatments, how we find that? Okay, we find that we find that this is the method for that actually. So we have 56 minus because 4 56 minus 58. So what we have is found by squaring the difference between each treatment mean and the overall mean, and then multiplying each square difference by the number of observations in each treatment. This is the method. So how many observations in each treatment? So this is the one treatment, this is another treatment, and this is another treatment. Okay, because when we go from person to person, each person is called one treatment. Okay, so how many observations we have for each person? 4. So what we need to do is to find the mean of each treatment, means each person total. The mean under Wolf over all the 4 values is 56, and mean of all these values under White is 70. The mean of all the values under Carosa is 48. So basically, what we need to do is we find the mean, like for example, for Wolf, and then from that we subtract the overall mean, square it, then multiply by total number of observations in this treatment. Okay. Similarly, we do this for for White, and then do for Carosa, and add them up, and total we get is 992. So this is called a variance due to treatments. Okay, when we go from one treatment to another. Now random variation we can do is 90. How we do that? So basically what we need to do is we go from here all the way like this, go from here and keep subtracting the mean value of mean value I mean mean value of each of these treatments, basically, with square difference between each value and mean for each treatment. So here we are not subtracting like the overall mean from this thing. What we are trying to do is we are focusing on one this at a time. Okay, so let's start with Wolf here. We have for Wolf, we have mean 56. So 55 minus 56 square, right? And then we have 54 minus 56 square, 59 minus 56 square, 56 minus 56 square, and keep add them up all and keep adding going to now white. So the mean of this white is 70, right? Then we have 66 minus 70 square, 76 minus 70 square, and so on. And if we add all these values together, we get 90. Okay. Now, how we find F statistic for that? So we have 990 divided by 2, and that's numerator, because bigger value goes on numerator and smaller value goes on denominator. So why we have 2 and 9 here? So 990 into 2 minus 2, because we total have how many treatments we have total? 3. We got 1 Wolf, 2 second white, and third Crossa. So total number of treatments we have 3, right? And 3, and how we basically degrees of freedom, how we find them? How we find? We have n minus 1. So we divide. What we do is we do is n minus 1. Total 3 minus 1. Total 3 minus 1, and we got 2. 3 minus 1, 2. So we have 992 divided by 2 here. And how about this bottom one here, 90 divided by 9? Why we have a 9 here? This is due to random variation, right? So in this case, random variation, what we have is total number of treatments minus, okay, let's see, total number of treatments. How many we have? 4 here, 4 here, 4 here. 4 times 3, 12. So we got 12, right? So it's 9 here. So we need to subtract 3 from 12 to get 9. Okay. And 3 means 3 or number of treatments. So right. So number of treatments. So we have total. We have a total 12 observations minus a total number of treatments. Total number of treatments is 3. So 12 minus 3 gives us 9. So that we can use this to find the F statistic. And we got this one as 49.6. Right. So now what do we compare that against? Because the ideal ratio has to be 1, right? 1. So so we compare against the value 1. Now, how close this ratio is to 1? Now the ratio is very different, far away from 1. Actually, this is a 49.6, way more than 1. Okay. So what we conclude from this now? We can conclude that there is a big difference in the mean number of customers served by the 3 employees. Okay, that's the conclusion. Okay, so that was an overview of analysis of variance. I hope this is clear to you in how to use this. And we discussed this, the basic underlying theories, underlying concepts, and we looked at a few examples, we learned through examples actually how to apply what we learned from theoretical conceptual knowledge, and how we apply that, and how we get the results we need. Thank you so much for watching, and hope to see you in another session like this. Thank you so much. Bye now.